Welcome back to another BGCSE past paper review. Today we're reviewing a chemistry paper. This is a paper 3 from the year 2019. Again, as always, please remember to write a school number, write a candidate number, and also write your surname along with your initials. Also, please to ensure that you read through the instructions carefully, and if you have any queries, please clarify them before you start the examination. There are also some important information given here, for example, STP, temperature, and also the certain pressure. Also, the volume of a gas, 1 mole of gas at RTP is given as 24,000 centimeters cube. So please refer to those if you should need them. And also there is a periodic table provided. You can also use that as well. All right, so jump into question number 1 from section A. It said sulfur is a substance that is produced at power plants. It reacts with oxygen gas to produce sulfur trioxide. Now, it's name the acid formed when sulfur trioxide reacts with rain. And so, if sulfur trioxide, when it reacts with water, which is simple as rain, then you get sulfuric acid. All right. And so, it said, what effect does this acid have on limestone rocks in the Bahamas? And if you have sulfuric acid reacting with limestone, which is a calcium carbonate, then it will cause a reaction and cause the rock to dissolve or to wear away. All right, so I'm just quickly providing the answers to make it quicker. And so question number 3 said write the balanced chemical equation for the reaction between this gas and water. So this is sulfur trioxide right here. And so sulfur trioxide reacts with water to give you sulfuric acid. All right, as shown right there. And then now for part B, it said that 0.0408 dm cube of a 0.16 mole per dm cube of this acid produced in A3 is reacted with 0.05 dm cube of potassium hydroxide. So use the acid from A3, answer the questions below. All right, and so here you say write the balanced chemical equation for this reaction. And so you're going to have the sulfuric acid right here reacting with the potassium hydroxide to give you potassium sulfate and water. And the reaction is as balanced as shown right now. All right, so again, you can also pause and make sure you have the information. So in part 2 now, it said determine the moles of the acid. So the mole of the acid, so first and foremost, what you need to do to get this is to know that the mole is equal to molar concentration multiplied by volume. And so the molar concentration based on the question, go back to the question and you can see both of them at the same time. So the molar concentration here is 0.106 moles per dm cube, and the volume is 0.0408 dm cube. So you multiply those, what you get is the mole. All right, so again, mole is equal to molar concentration multiplied by the volume. All right, and so you have to be careful with concentration as well, because sometimes you can have the mass concentration. And so you have to have mass concentration to find the mole. All you need to do is to multiply that by the mass of the substance. All right, so you have to look out for that as well. All right, for the next part of the question here, which is part 3, is to determine the concentration of potassium hydroxide solution. And so what you're going to look at is the equation and look at the molar ratio. So the molar ratio for this equation here, and we're going to compare here the potassium hydroxide here. So potassium hydroxide is 2 and the ratio of the acid is 1. And since you know the mole of the acid already, which is 0.043, then what we need to do here now is to multiply this by the mole of the acid by 2 to get the mole of the potassium hydroxide. And so therefore we have 0.043 multiplied by 2 to give us 0.086 moles of potassium hydroxide. Now, since you have the mole of potassium hydroxide to find the concentration, all you need to do is to divide that mole by the volume. And let's go back to the question. You're going to see the volume of potassium hydroxide right here. And so the volume of potassium hydroxide is 0.05 dm cube. And so once you divide the mole by that, then you get 0.043, sorry, you get 0.172 moles per dm cube. All right, and so that is the concentration of potassium hydroxide. The next part of the question state is a state one other effect of acid rain on the environment. And so these are some of the other effects even though you have more effects. So generally, you have damage to buildings, you have depletion of nutrients in the soil, damage to plant leaves. You also have an increase in the acidity of the ocean as well. And so for the last part of this question, it said name another gas that is responsible for acid rain. And so you have a choice right here. You have carbon dioxide, or you could also write nitrogen dioxide. All right, so those are your choices right there. All right, let's go to another question now, which is question number 2. And the question number 2 said non-metals are important industrial chemicals. It said the following non-metals are used to make a variety of other useful chemical substances. Use the non-metals listed to help you answer the questions that follow. And so the non-metals that are listed, we have carbon, we have oxygen, we have chlorine, and we have hydrogen. So all the questions will be based upon these 4 non-metals here. And so for part A, option 1, it's a write the anode half equation. So write the anode half equation or reaction for the electrolysis of molten lead chloride. And so at the anode, which is the positive electrode, the negative ion, which is chlorine, will be discharged there. And so based on this reaction, what you're going to have here, you're going to have 2Cl, 2Cl minus, so this is the ion, Cl minus is ion. And so for it to become a neutral atom, then since it gained an electron to become negative, they have to lose those. So there's a loss of electron right here. So electrons are now lost. And so you have chlorine gas formed and also the free electrons. And so this process is called oxidation, because oxidation is the loss of electrons. All right, and so for part 2 now, it said allotropes are different forms of the same element. And so if allotropes are different forms of the same element, it's a name the non-metal found as an allotrope in the atmosphere. And so oxygen is that allotrope that is found in the atmosphere as a non-metal. And so the forms that they exist in will be ozone, which is O3, and also diatomic oxygen. You just say oxygen gas generally, and that is O2. All right? And so for part 3, it's a state 1 product of the electrolysis of brine, and brine is salt water, right? And 1 use of this product. So once you put brine in an electrolytic circuit, what you might get, you're going to get chlorine at 1 electrode. You may also get sodium hydroxide, and you can also get hydrogen gas as well. So these are possible 3 products coming from the electrolysis of brine. And so if you get chlorine, the chlorine can be used to make bleach, for example. It can also be used in pesticides as well, just to make mention of that. And also sodium hydroxide can be used to make soap. You can use that to make soap. Hydrogen gas can be used to refine a fluid. Also, sodium hydroxide can also be used to make dyes and also used in paper production. Hydrogen gas also, again, as mentioned, can use in refining fuel and also used to make fertilizers as well. All right, so there are many uses. Once you have any suitable use, then you should be fine. Now for part 4, is a substance that acts as a reducing agent in the extraction of iron from its ore. And so carbon is a non-metal that is used, but it is used in the form of carbon monoxide, because carbon monoxide is actually the reducing agent, all right? But carbon is the answer. All right, so for part 5, it said this gas is the lightest, but is not used in inflatable balloons. It said name the gas and explain why. And so the gas here is hydrogen, and is of course the lightest gas. But the reason why it's not used in inflatable balloons is that it's very reactive, it is explosive, and react readily, and also highly flammable. So imagine you have children with inflatable balloons with this gas that can be ignited really quickly and also react readily. So and that could cause a serious problems. So it is a hazardous issue not to use it. All right. So for part B now, the elements are found as isotopes, right? And the mass of each element is based on the average of the masses of its isotopes. It's a determined isotopic mass of oxygen if oxygen 16 has a relative abundance of 99.8% and oxygen 18 has a relative abundance of 0.2%. And notice the total here be 100%, right? And so to work this out, you're going to go with the 16, the mass number here, 16. So you're going to say 16 multiplied by 99.8. And so you get a 15.968. And so you can do the same thing for the other oxygen, which is 18 times 0.2. You get a total here of 0.036. So when you add both of them together now, which is the 15.968 plus the 0.036, what you get there is 16.004 grams. So that will be the isotopic mass of oxygen. All right, let's go to the next part. Part C. It says sulfuric acid is an important acid made from sulfur. List two other properties of this acid. And so for sulfuric acid here, it is colorless. It is a strong acid, generally of a pH below 3. Also is corrosive. Well, all acids are corrosive. It also have a high boiling point. So you have a high boiling point, and again is an ionic compound. So generally ionic compounds, they do have high boiling point. And the general thing with sulfuric acid, it reacts with different type of bases to produce sulfate salt. So the salt will always be a sulfate. So whether it be like potassium sulfate, calcium sulfate, but the salt is always sulfate. All right. Next part of this question now, let's jump into it, which is the next question actually. And question number 3 is it identify the substances A to G. All right, and so this is a very lengthy question, and this is one of the reasons to actually skip out the part of typing. So it'll be really easier to really work through because this is a lengthy paper. All right, and so A1 is allotropes are different forms of the same elements, right? It's a solid A is an allotrope of carbon used in pencils. All right, and once you say using pencil, you know that is graphite. Okay, so that's like just a clue right there. So giving you some clues as I go along. It said reacts with excess of a gas, which is B, to produce gas C. Gas B is the most abundant element on Earth. So they give us a clue right here that gas B is the most abundant. A is used in pencil, not as graphite. The most abundant gas on Earth is oxygen, and it produces gas C. So carbon react with oxygen, going to give you carbon dioxide. So here now we know that A is graphite, B is going to be oxygen, and C will be carbon dioxide. So already we know those answers, right? Now for part 2 here, is a solid D is a green coating solid, also known as patina or verdigris. And once this is formed, it's on the statues, I made a certain of a certain metal. Is that this green solid reacts with dilute nitric acid to produce blue solution E. So you're gonna remember now that solid D will react with nitric acid, all right, to produce a blue solution E. Water and gas C. So, all right, so now we have a problem right here. This is saying sulfuric acid and this is saying nitric acid. Now there's a typo in one case. So let's work with sulfuric acid as in the equation, even though nitric acid can also use, but the problem with nitric acid, right, is that you get a blue substance as well, definitely as well. You will definitely get a blue substance. But let's work with sulfuric acid as an equation, all right? But we're going to work it out and talk about it, the possibilities, why nitric acid and why sulfuric acid may be the preferred choice right here. All right, so we're going to work with sulfuric acid. Again, nitric acid can also be used because the substance will produce a blue substance, but the most prominent blue substance that is formed is because of a sulfate. And so statues generally made up of copper, right? And so copper sulfate, if you think about it, the copper sulfate will be blue. So sulfuric acid reacting with copper, you will get a blue substance, right? So I just want to point that out. So that's why I'm sticking more to sulfuric acid rather than nitric acid. All right. Even though copper nitrate is a blue substance as well, but a prominent blue is copper sulfate. All right, so here we know that now the solid that we're going to have here is going to be copper carbonate, right? So copper carbonate will form. I'm going to tell you why copper carbonate. And copper carbonate is formed because first, the solid is copper. Copper reacts with oxygen to give you copper oxide. But copper oxide is more like a reddish to black. It moves from red to black, a matter of fact. Right? So you get a dark color. And so if copper oxide reacts with carbon dioxide, you get copper carbonate. All right, and so you get copper carbonate as a solid, just to kind of point it out. A matter of fact, I could even show you the reaction. let me show you the reaction on this side, since I've done most of the typing, which is great. So first you have is copper, and copper will react with oxygen, all right, in statue to produce, again, copper oxide. So what you get here is copper oxide, but copper oxide is reddish to dark, so a dark reddish thing. So really dark, actually. So let's say black. All right, so it's dark or black. It is black. So you're going to move from reddish color, which is the prominent color for copper, is kind of reddish. So you're going to get black. And then what's going to happen now is that this copper here, let me put it on this side right here. So this is going to react now with with carbon dioxide. Let's put carbon dioxide there. I'll put my oxygen on top. So let's take this out and put carbon dioxide. So the copper oxide now is able to react with carbon dioxide. So you get CO2 right here. And what you get as a result of this is copper carbonate. So you get CO3. Okay? So just to make a note right there. All right, so that's exactly what's going to happen here. And copper carbonate is green. So this is black. The copper oxide is black, but copper carbonate is green. All right, so let's go to the next part now. It says compound F contains a metal ion which forms a white precipitate with sodium hydroxide and ammonium hydroxide. They said the white precipitate is insoluble in excess sodium hydroxide and excess ammonium hydroxide solution, actually. They said the metal also burns with a bright white dazzling light. And once you see metal burning with white dazzling light, you're sure that is magnesium, right? So magnesium is that burn that bright dazzling white color. All right, and so it said now the negative ion in compound F reacts with silver nitrate and dilute nitric acid to produce a pale yellow-green precipitate. All right, and it said the negative ions is also used in photographic film. And so right here, you know that this is going to be iodine or iodide ion. So the iodine is going to be used right here, or the iodide ion. So the ion is actually iodide if it's a negative ion, so iodide. All right, so I'm just put, matter of fact, let me just put I minus there because iodide ion, okay? All right, so kind of working all through and then put, matter of fact, when I finish, I'm going to put all of them on it, all right? Then again, I'm also going to skip out the part of typing all that. So you're going to see the answers up now. Now, compound G is a fertilizer. All right, it's in sodium hydroxide. If sodium hydroxide is added to a sample of this fertilizer and warmed, ammonium gas is produced. They say the negative ions can be identified by adding barium chloride and dilute hydrochloric acid to another sample of the same fertilizer. The negative ion gives a positive result by producing a white precipitate. And it's identify the lettered substances, and again, we added the most of them. But the compound here as a fertilizer. And again, if it reacts with sodium hydroxide and warm, you get ammonia gas. So you know that this must be a nitrate. All right, must be a nitrate fertilizer. So again, A, as mentioned in the first equation here, A is the solid is going to be graphite. Gas B is oxygen and carbon dioxide. All right, so those are first three answers there. We have copper carbonate, as I show you in the reaction, that copper reacts with oxygen to form copper oxide, then reacts with carbon dioxide to form copper carbonate. And what you get as a result here as a blue substance is copper sulfate. And then we have magnesium iodide is compound F because of the two different ions that we identify. We identify magnesium and iodide, and so therefore is magnesium iodide as compound F. And then now for G, it is either ammonium nitrate fertilizer, or you can just generally say ammonium fertilizer, all right? Just to make a note of that. All right, so, and a matter of fact, the nitrate is the most important one because nitrate is a negative ion. I must only assume that is ammonium fertilizer because the most common nitrate fertilizer. But the negative ion that was outlined in part 4 right here, it is all indicating that it is a nitrate, all right? So, but compound G, as I'm saying, if a compound is a fertilizer, then I'm going to say it's ammonium nitrate. All right, because that's the most commonly used nitrate fertilizer. You also have potassium nitrate used again, but as I'm saying, the one that is most used is ammonium nitrate. All right, so for part B, you know, so write a chemically balanced equation for any of the reactions described in 1 to 5. And so I give you two options. The two easiest one, which is two first equations, I think. All right, the two first equations are two easiest equations. So the first one was, again, graphite reduces carbon. Carbon react with oxygen. And what you get as a result there is carbon dioxide. All right, so just to make a mention of that. And then the other option you have right here is one which is in part two, is copper carbonate reacts with sulfuric acid to give you copper sulfate, which is the blue substance that indicated water, and also carbon dioxide. Remember that an acid reacts with a carbonate, you always get a salt, water, and carbon dioxide. All right. Now for the next equation right here, which is it's a two molecules or 2 moles of copper reacts with oxygen gas to produce 2 moles of copper oxide. It's a calculate the mass of copper 2 oxide made from 127 cube of oxygen gas at RTP. So the first thing I'm going to do right here now is to make a note that volume is equal to mole times the condition, and the condition we're working here with is RTP. And so the mole of oxygen is going to equal to the volume of oxygen divided now by RTP. So make mole be the subject of the formula. And so therefore we have the volume here, which is given as 120, divided by the volume of 1 mole of gas at RT, which is 24,000. That was given the first cover page or the first page. And so that equals to 0.005 moles. All right. And so once you have a mole of once you have a mole right there of oxygen, that we're going to do, look at the mole ratio now. So look at the mole ratio, and the mole ratio is a 2:1 of copper. So we're going to find now the mole of copper 2 oxide now by multiply the mole here with the 0.05 by 2, you get 0.01. Also now, we can, from that now we're going to find our molar mass of copper 2 oxide, and our molar mass of copper 2 oxide is 80. All right, and so the mass of copper now will equal copper 2 oxide is 0.01, which is a mole, multiplied by the relative molecular mass or the molar mass. And so 80 multiplied by 0.01 gives you 0.8 grams. And so that is the mass of copper. All right, so now let's go to question number 4. And this is the last question in section A. It says the diagram below shows the electrolysis cell, which is used to extract aluminum from its ore. Now, here you have some positive carbon anodes. So these are carbon anodes, just to make a note here. We have our aluminum right here. We have aluminum outlet, and we have our steel container. All right, and we have a negative carbon on cathode. So the negative electrode is called the cathode. The positive one is called the anode. Remember that anode will attract ions, which are negative, and cathode will attract cations, which are positive. All right, and so let's look at option A. So option A, which is 1, is the extraction of aluminum from its ore is an expensive process. It's to give one reason to support the above statement. And so you have 2 possible options here you can mention, even though there are others that you can actually get into. But one is that the carbon anode must be replaced frequently. And so to replace the anode frequently, then you know that that will be costly over time, right? And again, for this process requires a lot of energy as well, or a lot of heat energy to really make this reaction possible. And so not even that, the aluminum oxide, that's one of the major problems. The aluminum oxide really requires a lot of heat. And this, I'm talking about 2,000 degrees Celsius, over a matter of fact, more than 2,000 degrees Celsius to melt aluminum oxide. So to get that amount of energy or heat, then you have to spend a lot of money on especially electricity or whatever source of energy that you're using. So it can be really costly. All right, and again, it's not just a direct reaction as well, because you have to go through stages, and to ensure that you do the extraction process, you have to make sure that before you even get to the electrolysis cell, you have to make sure you obtain the bauxite. You have to dig for that. You have to transport it, right? And then you have to separate the impurities and all of those things. So it's a long process. It takes time and goes through stages. Now for part 2, it's to write the name and formula of the aluminum ore. And with aluminum ore, it is bauxite is the name of that ore. And the formula is Al2O3 and dot 2H2. Okay, so that's the amount of water that is inside of the molecule. All right, and so for part 3, it's a name the chemical used to remove solid impurities from the aluminum ore. And so sodium hydroxide is used. And just to make a note that sodium hydroxide, it must be hot and and or concentrated. Matter of fact, let's say hot and concentrated, right? Both of them, not or, but and concentrated. Matter of fact, you know what? Let me even change that because it's and concentrated, not or, because you need it to be really concentrated and hot. All right, so for part 4 now, it said the half ionic equation shows the reaction at the cathode for 2 moles of aluminum ions. And so you see the 2 moles of aluminum ions right here. Again, they go to the cathode because their cathode is negative. And so the reaction here gives you 6 electrons plus the aluminum. It said write the half equation for the reaction of 4 moles of oxide. So we're talking about 4 moles. That's very important here. 4 moles of oxide ion at the anode. So we're going to work with 4 moles, and this is oxygen is happening there. So at the anode, oxygen will be discharged, and so therefore 4 moles of oxygen. And remember that the oxygen is a 2 minus as an ion, and then it will convert into oxygen gas and 8 electrons. And why 8 electrons? Because if you multiply the 4 by 2, you get 8 electrons over here, right? And so if you multiply here again, saying 4 oxygen, so therefore 2 times 2 is 4 oxygen as well, right? So the equation is balanced in that way. For part 5, it's a name the type of chemical reaction that is occurring at the cathode. And at the cathode, you have a reduction reaction because there's a gain in electrons, right? So aluminum gain electrons at the cathode, all right, and become aluminum ion. And so it is an reduction reaction, so gaining of electrons. All right, so for part 6, it says, why is the carbon anode replaced periodically during this process? Remember to say even this is why it is expensive. And reason because it becomes eroded because oxygen reacts with it, forming carbon dioxide. So oxygen will react with the anode and form carbon dioxide. So again, it will decompose over a period of time. All right, and part 7, this is a lengthy question here. Is the iron is extracted by heating with carbon, but aluminum is extracted by electrolysis. And he said why? And so aluminum is really too reactive, or again, aluminum is more reactive than carbon. And so what I'm going to show you quickly is the electrolysis series that you can actually use to guide you in terms of what will use heating with carbon or what will use electrolysis. All right, so let me just run through it real quickly on the side right here. So I'm going to put them on the side real quick. And so let's start with here with K, which is potassium. So yeah, potassium first. Then you go to sodium, which is Na, and then you go to calcium, and then you go to magnesium. All right, and magnesium, and then you go into aluminum, and then aluminum, then you have carbon right there. So carbon, I'm going to make a box around carbon so you know that that's what we're going to work with. Then you have zinc, and after zinc, you'll have iron, and after iron, you'll have tin, which is Sn. After tin, you will have lead, which is Pb, and then again, you're going to have hydrogen there, which I'm going to put a box around that, and then you're going to have copper, and then you're going to have silver, and then you're going to have gold, and then the last one, you're going to have platinum. All right, so PT. All right, so this is a series right here I'm showing you, and so this is very important for you to understand. So whatever is above carbon must use electrolysis. All right, and so we have hydrogen right here. These some would highlight them. All right, so these are standard right here. All of them up here must use electrolysis. They must put E. Electrolysis must be used right there. Again, because they are really reactive. All right, and they are more reactive than carbon. These here, between here and here, these you can use heating with carbon. So I'm going to put HC. All right, so use heat energy, and you use that with carbon and put carbon in bracket. Okay, yeah. All right, so just to mention that, and then the others here, they normally can be found inside of the earth, generally, sometimes that are unreacted or by themselves in a natural form. So you might find gold easily. When I say easily, I don't mean you're gonna find gold like that, but you see it by itself, which is uncombined state with any other substance. All right, so just to make a note of that. All right. So going to the next question, which is part B, is explain. Matter of fact, let me kind of erase this tail end right here. And look real funny. Oh, cool, that's better now. Right. So part B now said explain the following observation based on the properties of aluminum. Is the fences made of aluminum do not corrode. And the reason why they not corrode is simple because again they are corrosion resistant or they do not rust. Simply because aluminum do not readily react with moisture. So that's why it is used. It's a corrosion resistant, do not rust easily, and simply because it do not react with moisture readily. Now, airplanes, trains, and buses are made of aluminum, and the reason for that because aluminum is light, and so if you use heavy metals in moving objects for or transportation, then the heavier it is going to use more energy to move the to move it around. All right. And so easily form into shapes as well. So whatever form the plane going to be or the bus or whatever you're making, you can easily bend the aluminum to kind of make that design. All right. So what we're going to do now is to jump into part B. And let's jump into part B real quick. And again, I've already worked through the answers already in part B. So again, we're going to work through it quite fast and easy. All right. So for part B here now is to answer any two of the following questions, and so you have a choice to answer any two. And so the first one here, which is number 5, is a student carried out an experiment to investigate the rate of reaction between an excess magnesium carbonate and 50 centimeters cube of dilute nitric acid. Magnesium carbonate was in small pieces. Now the reaction is written in the form of an equation, and so we have magnesium carbonate reacting with nitric acid here to give you magnesium nitrate, water, and carbon dioxide. Again, you know that carbonate reacts with acid, produces salt, water, and carbon dioxide. The order is not really important because you can put the carbon dioxide first. It's just that it must have the reactant and products and their appropriate sides. Now, he measured the volume of carbon dioxide given off at regular intervals at RTP. The results are given in the table. And so looking at the table, you see the time in seconds from 0 all the way to 130, and then the volume of carbon dioxide from 0 all the way to 100, right? And of course, you can see the pattern here. The last three, they are the same values. All right, and so let's go down here now. Is a student use a conical flask, rubber tubing, and a gas syringe for the experiment. Name one other apparatus that is missing from the list. And so I put a few right here. And so just to kind of make you see everything at once, let me kind of go for a little bit more. Right. And so what is happening here, if you notice, we can use a stopwatch, and we need a stopwatch to measure time because time was checked. All right. You also need a measuring cylinder to measure the volume of the acid. That was not mentioned there as well. I need a rubber stopper, and the rubber stopper is to insert the rubber tubing into the flask. And so what I'm going to do is to show you how this is set up so you kind of an understanding of exactly what I'm talking about. So let's go to that right now. So the apparatus should set up like this. So you notice the rubber stopper was not mentioned at all. The stopwatch was not mentioned. And also here, again, we have our nitric acid, which is 50 centimeters cube. So we have to measure the volume before putting the conical flask, right? And so we need those three things. All right, so the apparatus should set up like this, and the volume of gas will be collected over a period of time. Again, the highest was 100 based up on the chart. All right, so let me work through this. Now, it's a plot the result in the table on the graph paper and label it A. And so here now would be, again, I've pre-draw this real quick to save some time. So your graph will shape like this, increasing going there. And then what I want to point out is that the last 3 points, they are the same. So the graph will plateau at from here to here. Okay, so there's a plateau of the graph right there. All right, so that would be a graph. Again, what I want to point out, I notice I put a title there, that the volume of gas against time. Also, I label both axes. I'm going to point out what you're going to get the marks for. You need to label the axis with units as well. So both X and Y axes, they are labeled. Also, you need to use fine lines, fine, neat lines, not no zigzag line. And your dot and your points must be pointed and clear. Okay, not no just big bubble like that, right? So you need to make a graph look appropriate. Now, for the next part of the question, this part 2 is to find the volume of gas produced between 10 and 15 seconds. And so at 10, if you go on the graph, at 10, it will be the 27 right here. And then at 15, which is right here, halfway in the middle right here, come all the way up here, it will go all the way up to 38. All right. And so it will be 38. And so what you do is a minus 27 from 30 to get 11 centimeters cube of gas produced between that. All right, now for part C, is on the same axis, sketch a graph to show the expected result if the experiment is repeated with the same amount of magnesium carbonate in small pieces, but 50 centimeters cube of nitric acid at, and this matter of fact is half the original concentration. Label graph Y. And so just to make a note right here that if you use half the concentration, it therefore means you have half the amount of particles within the acid itself. And so if you have half the amount of particles in the acid, then the graph should look like almost exactly half to the original because the concentration is half. Now what I want to point out, if, and I should have put this one on as well, if the same temperature was used, however, right? If a different temperature was used, the reaction will only be a little bit slower, but you get the same end result. All right, just take a longer time to reach that 100 degrees, 100 centimeters cube. All right, so you get the graph will come all the way up here and then tapered off somewhere over here. All right, if the temperature was lower. But since the concentration, they're talking about the concentration is half, then they produce half the amount of substances. All right. For part D, is explain in terms of kinetic theory what would happen to the rate of reaction in the first experiment if 50 centimeters cube of the acid was cooled down to 10 degrees Celsius before magnesium carbonate was added. So now you use a lower temperature. So now, based on this, the particles in the acid will lose kinetic energy, again because they cool down. Remember that temperature and kinetic energy, they are proportional, right? And so if you have a decrease in temperature, therefore, there's a decrease in kinetic energy. And so if a decrease in kinetic energy now, it results in a slower movement of the particles. And if you have slow movement of the particles, then the particles will collide less, reducing the rate of reaction. All right, so look at the question and the answer right there at the same time. All right, next question, notice part E. For part E, it said explain what would happen to the initial rate of reaction and the total volume of gas if magnesium carbonate was in one big lump instead of small pieces. So you have one big lump, and so if you have one big lump, what this simply means is that there is a less surface area. The surface area decrease. Okay, so if magnesium carbonate is in one big lump, it means that the surface area for reaction is reduced. All right, smaller pieces, greater surface area. So the initial rate of the reaction would be slower for sure, but it also asks us what will happen to the volume of gas. The volume of gas would be the same because again, the only difference is that the reaction is faster because of smaller pieces, but eventually the big clump or big lump will eventually all break down, right? All right, so however, it does take a longer time to produce, but the volume will be the same. Part F, it said the excess magnesium carbonate added was 0.2 grams. It said use the equation for the reaction to calculate the mass of magnesium carbonate that actually reacted with the nitric acid. And so here it said based on the second, I've used this based on the second graph because when I use the first graph and I get 100, then what I realize I end up getting more than the 0.2. So what I do is to revert to the second graph. And the second graph here, it produces, based on the second graph, which is half the concentration, you get half the amount of carbon dioxide produced. And so I use 50 centimeters cube of carbon dioxide produced. And I'm saying is that RTP. So therefore, if I divide this by 24,000, this is supposed to be 24,000. So let's put a next zero right here. So this will be 24,000, not 2,400. All right. And so what you get there is actually 0.02. Okay. So the value there is actually correct, 0.02. And then now, once you get that amount of moles, what you're going to do now is to actually find out the moles of magnesium carbonate. And so based on the molar ratio, all right, so based on the molar ratio here, which is the same molar ratio, 1-to-1 ratio, then what you're going to do now is to get, so okay, 0.02 multiplied by 84, and 84 is the molar mass of magnesium carbonate. And as a result of that, what do you get here is 0.17 grams. All right, so that is the amount of mass of magnesium carbonate that was actually used up in the equation. All right, so now let's go to the next part of the question. Now, next part of the question is to find the mass of magnesium carbonate remaining as excess after the reaction completed. So again, the excess amount of magnesium carbonate was 0.2. The actual amount that was used is 0.175. So if you minus what was used from what you actually put in, then what you have remaining is 0.025 grams. Now for part G now, it said that there are concerns that human activities may be increasing the greenhouse effect, leading to global warming. One of the gases that cause the greenhouse effect is carbon dioxide. Name on the gas that cause global warming. So global warming should be right here. Again, there's a typo. All right, so methane and nitrous oxide are two options that you can actually put one of those. All right, so methane gas and nitrous oxide, they are greenhouse gases. Now for part 3, is identify one means by which carbon dioxide can be removed from the atmosphere naturally, and write a word equation for this. And so it can be removed by photosynthesis, that's the natural way. And so water plus carbon dioxide give you glucose and oxygen. Another way that carbon dioxide can be removed from the atmosphere is also by the absorption within the ocean. All right, but that also leads to ocean acidity. All right, and again, when carbon dioxide reacts with water, it becomes an acid. All right, I remember we talked about that type of reaction already. Now for number 6, it's the data shows the boiling points and formulas of some alkanes. It's a write the missing formula of the missing alkane and predict the missing boiling point in the answer booklet. And so here we have methane and here we have ethane. And so the missing thing ranges from about 86 to 90. So any number between that will be pretty much correct. But what you need to know that it must be less than this. So if you're not sure what you can put is say that is less than 168, right? So if you're not sure about the exact value, you can just put is less than 168. And also greater than so it's great is actually, I should say, greater than 164, right? But it's also less than negative 42. All right, so you can make sure you put that right there. So if you don't know, it is range between again more than 160 minus 168 or less than minus 42. All right, and so here, okay, right here now. So the other one in this series right here, so after 3 carbon is 4 carbon. And then again, each carbon, the difference between H's is 2, if you notice it. The difference coming all the way down the pattern is 2. Because remember, this is a homologous series, and homologous series, each member separate from the other by a set number. Okay? So if the other carbon here is 4, then the H must be 10. And so even if you remember the formula for alkane, it is CnH2n plus 2, so you can use that as well to kind of work out how many H's. Or you can just look at the pattern in the circuit. This is 4, this is 6, you add 2 to it. This is 8, you add 2. And then here must be 10, add 2, 12, then add 2 more is 14 and 16. All right, so each member is separated from each other by a set number. That's what the homologous series is. Now for part 2, it said what is the relationship between the number of carbon atoms in the hydrocarbon and its boiling point? And so if you look at it, it said, if you look at the chart again, you would realize that as the number of carbon increase, the boiling point also increase as well. So look at it carefully. Moving down the list, the boiling point is increasing. All right. So as the number of carbon increases, the boiling point also increases. Now here, part B is a propane is used as a fuel for cooking. Write a chemically balanced equation for the complete combustion of propane in excess oxygen, producing carbon dioxide and water. And so again, propane is C3H8. You write that with water, with oxygen, what you get is carbon dioxide, water, and you get energy as well. And this is how the equation is actually balanced. I put the state symbols there as well. Practice doing those things. Write the state symbols. These are all gases going to form. All right, just to make a note right there. All right, next here, it said use the equation to calculate the volume of oxygen required for the complete combustion of 20 dm cube of propane gas in a gas tank. And so the first thing to do is convert the dm cube into centimeters cube. They're supposed to be centimeters cube. That's a typo right there and my mistake. All right, so that's a centimeters cube. So what you need to know that 1 mole of a gas, we're going to convert that into centimeters cube. And so what you're going to do is to multiply the dm cube by 1,000, you get 20,000 centimeters cube of the gas. So what you're going to do now is to find the mole now of methane is the volume here divided by the value of at RTP, which is 24,000. So once you divide that, you get 0.836. All right, just to make a note right there. And so based on the mole ratio, we know is a 1 to 5 based on the equation. So based on the equation, the molar ratio is a 1 to 5. Notice it there. All right, so 5 for oxygen and 1 for the propane. All right, so once based on the mole ratio, now what we're going to do is to find the mole of oxygen now by multiplying the mole here by 5. And so therefore, if you multiply mole by 5, what you get is 4.165 moles. And so what you're going to find now is that once you have the mole, you can find the volume of oxygen now. And you're going to multiply the mole by the RTP value. So if it's 4.165 moles, then you're going to multiply it by 24,000. And so what you get is 99,960 centimeters cubed. Or if you divide it by 1,000, what you get is 99.960 dm cube. So you can work it like that. And just to show you again, just to go back up one more time to show you something. What you actually could do, you could actually keep the dm cube if you want, but you have to convert the 24,000 in dm cube, which is 24 centimeters cube. You could have done that as well. All right, so there's no one way to do it. All right, now part C is that what is meant by cracking and how it is important to the oil industry. And so cracking, for 2 marks, cracking breaks down or decompose large hydrocarbons into smaller ones. An example of that is alkanes, and you normally get an alkane and an alkene. And so why is important to the industry as well? You can actually get to produce refined gas. All right, so you get refined gas or gas that are more flammable, because remember now, the larger the hydrocarbon is the more solidified the substance becomes. So getting smaller number of carbon now become more gaseous, all right, and become more flammable as well. All right, so that's how it's important. All right, going to the next part of the question now, this part 2 is write an equation to show cracking of C14, H30, and this is tetradecane because it's 14, so it's tetra. Tetra means 4, decane is 10. So tetradecane here. And they said the product must be an alkane and an alkene and ethene as another alkene. So here they want us to have 3 things. And so there are many acceptable possibilities that they can actually have. So many possibilities of the answer, but I'm going to give you about 2 here. So let me give you 2 real quick. And so you have the tetradecane turns into ethene, heptane, and pentane. And pentene, because it must have another alkene, it said. Again, ethene, they say is a must. So I put ethene in the first one. And so again, the second option, you can have ethene, you can have heptane, and you can also have propene. All right, so any of these are actually options. Now, a way to do this actually can actually change the number of carbon from here, for example, I put 1 more here, but you can't change ethene because they say 1 must be ethene, right? So I could juggle between this. I could make this be 6, right? I could make this be 6, and this over here could also be 6 as well, so I could do that as well. So there's many ways you can actually work it out, right? Just change the number of carbon and of course, the number of H's to make them appropriate. All right? Yeah, so you can do, there are many ways to do this. Many ways. There's no one way. For part 3, is when propane is being burnt in limited oxygen, it produces a smoky yellow flame. So if you have limited amount of oxygen, it said now what causes the yellow flame color? And simply because if you have less oxygen, what you're going to have is an incomplete combustion of the propane itself. So it's an incomplete combustion. All right, so that's what they're looking for. Number part D1 is whether they are natural fibers like cotton and silk or synthetic fibers like rayon and silk. They are all polymers. Plastic are also polymers and man-made. The starting chemical for polythene is monomer ethene. It's a copy, the structural formula of an ethene monomer to show the polymerization of this molecule to polyethylene. Display all bonds when drawing the structural formula. So I need to show you all the bonds here. So what I'm going to show you is this. All right, I put them in different color coding. So you're going to see. So here now, it's a use at least 3 monomers. In the diagrams, I use 4. All right, you could go with 3, but I just want to do 4. So this is what they gave you first as the ethene. And so we're going to make here, notice every 2 carbon. All right, so they join together and notice the double bond is gone and they all form single bonds, right? All right, because why they form single bond? Because they join together now, those spaces are actually used up to react with the other carbon. All right, so I just color code them for you to see that polyethylene right there. All right, here now it said write a chemically balanced equation to show the reaction between ethanol and ethanoic acid. And once I have alcohol and an organic acid reacting, what the form is an ester. And so here now the ethanol, which is the C2H5OH, plus the ethanoic acid, which is CH3COOH. What you get here is C3COO, CH2CH3 plus H2. And so this C2H5OH is ethanol, which is an alcohol. And then we have our ethanoic acid, which is an organic acid, and our ethyl ethanoate, which is the ester formed and water. All right, so that's just a breakdown of what is happening right there. All right, so that's to show you the entire question again. All right, let's go to the next part of the question here. It said, now, an organic compound X contains by mass 12.8% of carbon, 2.13% of hydrogen, and 85.1% of brine. It said determine the empirical formula, which are 3 marks here. Is and first step, I do this by steps, so I'm going to work through by steps. So the first step is to assume 100 grams of the substance, right? So you convert the percentage to mass. And so for carbon, it'd be 12.8 grams. For hydrogen, it'd be 2.13 grams. And for bromine, it would be 85.1 gram. And so notice I just convert the mass, the percentages to mass. Here now is to find the mole. Here is to find the mole of each element. And to find the mole of each element, here is just the, you're going to divide the mass given up here, or the mass worked up based on the percentage, by the relative atomic masses. And so carbon, the percentage or the mass that they worked out right here, divide by 12, we get 1.067. And for hydrogen, divide by 1, says get 2.13. And for bromine, it is 85.1 divided by 80, get 1.064. And so those are the moles of each of the elements. The next thing you're going to do now as a next step is to find the smallest whole number ratio by dividing each mole by the smallest mole. And so the smallest mole here, based on what we have up here, is 0.064. These are very close, however, so they could be taken as the same. All right. And so for carbon, you get here, you're going to get a little bit more than 1. It's going to be point something, but it's run out to be 1. And then hydrogen is 2. And then if you divide bromine, what you get there is 1 as well. So our empirical formula is CH2Br. Okay. All right, and so now compound X has a relative molar mass or molecular mass of 188. Find its molecular formula. And so again, I'm going to show you a little equation right here to use in this, and then I'm going to work out the steps. So the equation you can use is that the molar mass of the compound, which is 188, divided by the molar mass of the empirical formula, and then you're going to multiply it by the empirical molecular formula. So I want you to understand that. All right, so I'm going to put them in now, substitute here. So first, let us find the mole. We find the mole first we find the molar mass, I should say, or the relative molecular mass of the empirical formula, which is, again, the empirical formula was CH2Br, and so therefore we had 12 for carbon there. For H it is 2, and for Br is 80, so get 94 grams as the molar mass of the empirical formula. Now, based on the equation here that is in purple, again, we said the molar mass of a compound given, which is 188, divided by the molar mass of the empirical formula. Then you multiply it by the empirical formula right here, which is CH2Br. And so as a result, what you get, if you divide 188 by 94, you get 2. And so therefore, 2 multiplied by CH2Br, what you get is C2H4Br2. And this is dibromoethane. A matter of fact, this can be named a different way, depends on where the BRs will be placed, but I just put them on 1 carbon, so therefore I'm just saying it is dibromoethane. All right, again, it could be 1,2-dibromoethane. So there are many ways, well, there's another way, I shouldn't say many ways, but there's another way actually how to name it. It can also could be 1,2, depends on where you place the BRs. And so for part 3, say draw the structural formula for compound X, showing all the bonds. And so again, if it's 2 carbons, the carbons together, you have 4 H's, I distribute them like that. And I put the 2 BRs. Again, the BRs could be on 2 different carbons, and in that case, it would be 1,2-dibromoethane. Okay, just to make a note right there. Again, I have them on the same carbon, so just dibromoethane, and that's it. All right. Next, number 7 now, which is the last question. It's the Haber process produces ammonia, which is critical to all commercial farmers. And so you have a source here, which is liquid air, and then you have a source right here, again, that provides you with hydrogen, and the source of air right here produces nitrogen gas. Okay. All right, and so again, it goes under certain conditions, and the conditions you have a temperature which is 450 degrees Celsius. We have a catalyst, and then we have pressure, high or low. And so the question I'm going to ask you is to use the flow chart to answer the question below in the answer booklet only. And he said, right, that means what they didn't want to do is to write on the flow chart and present that as the answer. So he said, write the source of hydrogen, and the source of hydrogen is natural gas, for example, methane, right? So any natural gas can be used, but specifically they tend to use methane, all right? But natural gas is the answer. It's a given name of the catalyst used in the Haber process, and this is actually iron. So iron is used in the Haber process. It's a state whether the process requires a high pressure or low pressure, and it's really high pressure. All right, so let's go back there. So it's a high pressure. It's a rather balanced chemical equation for the overall reaction in the Haber process, and for 2 marks. And so the Haber process again uses nitrogen gas, nitrogen gas come from the air or the atmosphere, and with hydrogen gas coming from natural gas, and you get iron as a catalyst to produce ammonia. And of course, the reaction is balanced in this type of way. Notice a reversible reaction as well, and these are all gases. Now, for part 5, it's a 15 moles of hydrogen, right? 15 moles of hydrogen gas are reacted with excess nitrogen gas. Calculate the number of moles of ammonia that could be produced. And again, if you have 15 moles here, if you have 15 moles being used, just to make a note right here, the ratio here, as we know, is a 3-to-1 ratio, right? All right, so what you're going to do, if you have 15 moles, you divide the 15 by the 3. That's a 1. And so you have 12 moles of hydrogen right there, okay? And so you will have 12 moles. All that they ask you to find is the moles, really, right? Now for part 6, it said, in every cycle of the Haber process, only 15% of the ammonia is produced and the unreacted gases are recycled. So calculate the mass of ammonia produced in every cycle using your answer to A5 above at RTP. Now, the first thing here, remember that mass is equal to mole times the molecular mass, right? Or the molar mass. So in the theoretical mass that is produced here, it is 10 times 17. And why 10? Because they must go back to it, because we get 10 here. 10 moles were produced. All right. And then the molar mass is 17. Okay. So the molar mass here is 17. So the molar mass of ammonia, and ammonia is NH3. Okay. So they're going to be 17. Now the actual mass here is actually 170 grams, which is the 170 that is actually produced theoretically. You're going to multiply that now by 15%, and so actually you get 25.5 grams. So theoretically, if all of the substance were used up, then what you're going to get is a whole 170 grams. But they only say 15% of it is actually what is produced. So if you only produce 15%, then it's 25.5% grams that you actually get out. All right. Now, we say calculate the concentration of ammonia solution produced if your answer in A5 is dissolved in 200 centimeter cube of water. So if dissolved in 200 centimeter cube of water, what you're going to do now is to get the mole, and what they want to find is concentration. We already know the mole was 10. Now the volume is 200. So 10 divided by 200, what you get is 0.05 moles per dm cube. Based on the formula, concentration is equal to moles over the volume. Remember, there's a next way to find concentration as well. Just to mention that, what is the mass concentration, so it's mass over volume, but here we're talking about molar concentration. So it's going to be mole over the volume. All right, and so next part question right here, this is part 8 of this question. This is a long question here. It's for the Haber process to convert a high percentage of nitrogen and hydrogen to ammonia. The pressure may be increased by 100 atmospheres. However, this is not done. State one structural and one economical reason why this is not viable, why this is not a viable option. So increase the pressure will be excellent to get more ammonia produced, all right? And so a structural reason here, because equipment may not be able to hold or withstand such high pressure. And not only that, you may have also have explosion if it cannot contain the buildup of gas within the container. Economically, to compress the gas under such high pressure, you require a lot more energy. And to produce and to use more energy, of course, your electricity bill or whatever you're paying for will increase. So using a lot of energy for a small increase, for only a small increase in the product may not be profitable. So if you're going to get a larger increase now, yeah, that may make sense. But if a small increase, why bother? Right? Because you're spending much more than what you're actually getting out at a certain point. All right? So therefore, it doesn't make sense. All right, so for part B, it said in the contact process, a reversible reaction takes place between sulfur dioxide and oxygen. It's a write a balanced chemical equation for the reaction of sulfur dioxide with oxygen, include the catalyst. And so this is a balanced chemical equation here, and it's a reversible reaction for, again, the contact process. So let me just go back up a little bit here. See if I put, yeah, like that. So that's the contact process, everything together. All right. And so if you notice, the catalyst is also there as well, all right, which I'm going to talk about that just now at the bottom right here. Now we say, according to Le Chatelier principle, explain the effect on the equilibrium concentration of sulfur trioxide if the temperature of the reversible reaction is increased. So if you increase the temperature, what's going to happen is that the equilibrium position will shift towards the left. And this will result in a decrease in the concentration of sulfur trioxide to get less sulfur trioxide. And now for part 3 now, it said the concentration of oxygen is increased. If we increase oxygen, right? If you increase oxygen, then the concentration of oxygen is increased. The equilibrium position will shift towards the right, and this will result in an increase in the concentration of sulfur trioxide. All right, so just to make a mention right there. So again, based on Le Chatelier principle, remember, you always try to shift the equation. Also, always try to shift to maintain an equilibrium. So if you increase in one area, you're going to shift towards the other side and cause a buildup of that substance, or increase or decrease based on what is happening. All right, now it's a write a balanced chemical equation for the reaction of sulfuric acid with ammonia. And so sulfuric acid with ammonia, this is a balanced chemical reaction. What you get as a result is ammonium sulfate. All right. And now that's the end of it. And again, I'm here to just to say thank you. And I wish you luck in the examination. And I will see you soon. All right. Take care and be safe.